Okay, so today we're going to do this problem from Rudin 7.18, which says, let f of n be a uniformly bounded sequence of functions which are Riemann integrable on AB, and put big F sub n of x is equal to the integral from a to x of fn of t dt. And we want to prove that there exists a subsequence, big F sub n sub k, which converges uniformly on a comma b. And once we see this compact interval and we see which converges uniformly, and also of course this subsequence part, that immediately makes us think of Arzelà Ascoli, which tells us that if k is compact, if fn is part of the continuous real valued or complex valued functions, and fn is pointwise bounded, fn is equicontinuous on k, then that tells us that it's uniformly bounded on k, and also that this subsequence contains a uniformly convergent subsequence. And this is going to be the key part. So basically, if all of these conditions are true, then we can immediately see that big F sub n sub k is the uniformly convergent subsequence. So let's check all these conditions. So k is compact. This is true just because a comma b is our k here, and this is closed and bounded, so it's compact, so that's always true. Next, we see from theorem 6.20, f sub n x is continuous. So that is also true. And this is where it kind of gets tricky. So f sub n, so this sequence, is pointwise bounded. Well, we can't, it's kind of going to be hard to check at every single point of x. So instead of doing that, we can first see, is it uniformly bounded? And this is actually a lot easier to see, because what we can do is we can just take this and see, is it smaller than or equal to some constant, right? And if it's smaller than or equal to some constant, then we know it's uniformly bounded, and then we can say it's pointwise bounded. Okay, so we know that f sub n, big F sub n sub x in absolute value is just going to be equal to the integral from a to x of f sub n t dt. And notice that this is uniformly bounded, so this is always going to be smaller than or equal to some m in R. And thus we can take this m out. We can say that this is smaller than or equal to integral from a to x of dt. And that's easy. That's just going to be x minus a. Or I guess absolute value of x minus a, because the integral could be negative if x is less than a. And then that's just always going to be smaller than or equal to big M of b minus a. Okay, so this is always true because we know that x has to be between a and b. So this distance is always going to be less than or equal to this distance. And this is in R. It's a constant. So we have that it's uniformly bounded, and thus it's pointwise bounded. All right, so that also holds. And finally, we want to show that big F sub n is equicontinuous. Why is this true? Well, again, we can just, recall, by the way, that equicontinuous means that for all xy, where x minus y is less than delta, this implies that big F x big F minus y is less than epsilon for arbitrary epsilon for all n and n. So this should work for all the functions in this family. And for this, again, we do kind of a similar thing as up here. So big F sub n of x minus big F sub n of y. This is going to be equal to go from a to x of f sub n of t dt minus y n of t dt. And that's just going to also equal the absolute value from x to y. So you can just see, you know, if x is smaller than y, then it's going to be like this. Or I mean, yes, if x is smaller than y, or y, it's going to be equal to the absolute value of this. And then if y is greater than x, greater than x, then this would be negative, but we're taking the absolute value, so it doesn't matter. And that's just going to be, again, we can just see that this is smaller than or equal to m in R due to this uniformly bounded property. So we can take it out. Then that's just going to be y dt, which is and now we can see that if we choose our delta to be less than epsilon over m greater than 0, this is less than epsilon over m, these cancel, and then we get it's less than epsilon. So yay, all of these conditions hold, so we know that big F sub n contains a uniformly convergent subsequence, which means this holds, and we're done.